Now, let's start exercise chapter number 7. Example 7.1. A 100 ohm resistor is connected to a 220 volt 50 hertz AC supply. What is the RMS value of current in the circuit? B. What is the net power consumed over a full cycle? Okay. Now see, R, that is 100 ohm, that is given to you. Supply voltage 220 volt. We already discussed this thing. Whenever nothing is mentioned for the supply voltage, simply it is given to you voltage is this much. Always you have to consider that is RMS voltage. Clear? Frequency, that is 50 hertz for that supply. Now RMS current, that is equal to RMS voltage upon resistance. So I, that is V by R. 220 upon 100, you will get the answer. Clear to all of you? Now, net power consumed. So, net power consumed, that is average power during one cycle, and that is I square R. Whatever the value of I is calculated here, substitute. Then R is given to you 100, you will get the power consumed. Then example 7.2. The peak voltage of an AC supply, that is 300 volt. What is the RMS voltage? B. The RMS value of current in an AC circuit is 10 ampere. What is the peak current? Now here specifically it is mentioned this voltage, that is peak voltage. So we can write Vm, that is 300 volt. Now RMS voltage, V, that is Vm by root 2. So we can write Vm, that is 300 by root 2. Then we will get RMS voltage. Then B. Now RMS current is given to you 10 ampere. Now from that we have to find the peak current. So peak current Im, that is root 2 into I. Okay. Now root 2 into 10, you will get the answer. Clear to all of you? Then after example 7.3. A 44 millihenry inductor is connected to 220 volt and 50 hertz AC supply. Determine the RMS value of the current in the circuit. Now see example 7.3. Inductor with inductance L equal to 44 millihenry. So that is 44 into 10 raised to minus 3 Henry. Clear? V, that is 220 volt. So that is RMS voltage. Okay. And frequency of the source, that is 50 hertz. Now RMS current, that is RMS voltage upon. Now only inductor is there in the circuit. So we have to take inductive reactance here. So we can write I, that is V by XL. But XL, that is omega into L. And omega is replaced by 2 pi f. So I, that is equal to resultantly V upon 2 pi f L. V, that is given to you 220, 2 pi f, that is given to you 50, and L, that is 44 into 10 raised to minus 3. Solve this one, you will get the current. Clear to all of you? Example 7.4. A 60 microfarad capacitor is connected to a 110 volt 60 hertz AC supply. Determine the RMS value of the current in the circuit. Now see, capacitor, that is with capacitance 60 microfarad, so that is 60 into 10 raised to minus 6 farad. It is connected with the supply of 110 volt with frequency 60 hertz. Now RMS current, that is RMS voltage, means V upon Now only capacitor is there in the circuit, so we have to take capacitive reactance. Okay, so that is Xc. So resultantly we can write I equal to V upon Xc. But Xc, that is 1 upon omega c. So V upon 1 upon omega c. So that is V omega c. Therefore, we can write resultantly I, that is equal to V into omega, that is replaced by 2 pi f. So we can write I, that is equal to V into 2 pi fc. V, that is 110, 2 pi f, that is given to you 60 hertz, and C, that is 60 into 10 raised to minus 6. Solve this one, you will get the answer. Now example 7.5. In exercise 7.3 and 7.4, what is the net power absorbed by each circuit over a complete cycle? Explain your answer. So here,
sorry sir, later.
now here, for both the circuits given to you in 7.3 and 7.4, the phase difference between voltage and current, that will be plus or minus pi by 2. Clear? In case of inductor and capacitor, we can write when phi, that is plus or minus pi by 2, in both the cases, cos phi, that is equal to 0. So power absorbed, that is 0. Example 7.6. Obtain the resonant frequency omega r of a series LCR circuit with L equal to 2 Henry, C, that is 32 microfarad, and R, that is 10 ohm. What is the Q factor of this circuit? Simple thing. Inductance of the inductor, that is 2 Henry. Capacitance of the capacitor, that is 32 microfarad. So that is 32 into 10 raised to minus 6 farad. This circuit, that is 10 ohm. Now resonant frequency, that is 1 upon 2 pi root LC. So substitute here the value of pi, L and C, and then solve it, you will get resonant frequency. If you want to calculate resonant angular frequency, then simply you can write omega r or omega 0, that is 1 upon root LC. Simple thing. Now value of Q factor for this particular given circuit, we have the equation for Q factor, that is Q equal to 1 upon R root L by C. So R, that is 10, L, that is 2, and C, that is 32 into 10 raised to minus 6. Substitute all these values, we will get Q factor. Clear to all of you? Example 7.7. A charged 30 microfarad capacitor is connected to a 27 millihenry inductor. What is the angular frequency of free oscillations of the circuit? So capacitance, that is 30 microfarad, so that is 30 into 10 raised to minus 6 farad. Inductance, that is 27 into 10 raised to minus 3 Henry. Now frequency of free oscillations, F0, that is 1 upon 2 pi root LC. Substitute the values. 2 pi L, that is 30 into 10 raised to minus 6, and C, that is 30 into 10 raised to minus 6, and L, that is 27 into 10 raised to minus 3. Now if you want to calculate angular frequency, then simply 1 upon root LC. આ 2 pi નહીં લેવાનું આપણે, એને લેફ્ટ સાઈડ લઈ લો, એટલે that is omega 0. Then example 7.8. Suppose the initial charge on the capacitor in exercise 7.7 is 6 millicoulomb. What is the total energy stored in the circuit initially? What is the total energy at later time? So maximum charge on the capacitor that is given to you 6 millicoulomb. So 6 into 10 raised to minus 3 coulomb. Energy stored at time t equal to 0, that is electric energy, and later on, no doubt it transforms into magnetic energy, but the total energy that remains constant in this one. We discussed in LC oscillations. So U, that is Qm square by 2C, Qm that is 6 into 10 raised to minus 3 square of it, 2, then capacitance 30 into 10 raised to minus 6 farad. Okay, solve this one, you will get the answer. And later time, the energy that remains constant and that we discussed in the theory. Clear to all of you? Then after, example 7.9. A series LCR circuit with R equal to 20 ohm, L equal to 1.5 Henry and C equal to 35 microfarad is connected to a variable frequency 200 volt AC supply. When the frequency of the supply equals the natural frequency of the circuit, what is the average power transferred to the circuit in one complete cycle? Okay, now see. Resistance that is 20 ohm, inductance that is 1.5 Henry, capacitance that is 35 microfarad, so that is 35 into 10 raised to minus 6 farad. Supply voltage that is 200 volt. Now, say here, 7.9. When the frequency of the supply equals the natural frequency of the circuit, means indirectly it is given to you in the circuit, you are getting resonant condition. Clear? So when frequency of the supply is equal to the natural frequency of the circuit, resonance takes place. And when resonance takes place at that time, Xc that is equal to XL. So when Xc and XL becomes equal, then your Z that will be equal to R. Simple thing. Now, current I that is V by Z. But now your Z that is R. So we can write V by R. V that is 200, R that is 20. So current that is 10 ampere. Now, when Z equal to R, at that time, the phi that is 0. So cos phi that is 1. So power that is V into I. V that is 200. I that we calculated 10. So you will get answer 2000 watt. Clear to all of you? Then after 7.10. A radio can tune over the frequency range of a portion of medium wave broadcast band 800 kilohertz to 1200 kilohertz. If its LC circuit has an effective inductance of 200 microhenry, what must be the range of its variable capacitor? Okay. Now see, frequency band that is given to you, F1 800 kilohertz, so that is 800 into 10 raised to 3 hertz, to F2 1200 kilohertz, that is 1200 into 10 raised to 3 hertz. Inductance that is 200 microhenry, so 200 into 10 raised to minus 6 Henry. Now, we have the equation for the resonant frequency, because when the circuit is tuned, resonance takes place. Okay. So that is 1 upon 2 pi root LC. So we can write F square equal to 1 upon 4 pi square LC. Therefore, C equal to 1 upon 4 pi square LF square. Now, substitute here in this equation. Once F equal to F1, we will get C1. Then substitute F equal to F2, we will get C2. So C1 that is 1 upon 4 pi square LF1 square. So substitute in this one the value of L and F1 and take square of it and then solve, you will get capacitance. Then C2, that is 1 upon 4 pi square L F2 square. Substitute here the value of L and F2, then solve, you will get C2. Clear? So we can write here range of capacitor is C2 equal to this much farad to C1 equal to this much farad. રેન્જ લખવાની હોય ને ત્યારે સ્મોલ ટુ હાઈ એવી રીતના આપણે લખતા હોઈએ છીએ. અને આ બે ફ્રીક્વન્સીમાં જુઓ F2 is greater than F1 એટલે કે C1 that will be obtained greater than C2. એટલે આપણે રેન્જ જ્યારે લખીએ આન્સરમાં ત્યારે C2 to C1 એવી રીતે લખીએ. ક્લિયર ટુ ઓલ ઓફ યુ?
મારે સેકન્ડ અને થર્ડ ચેપ્ટરમાં થોડું
Example 7.11. Figure shows a series LCR circuit connected to a variable frequency 230 volt source. L that is 5 Henry, C that is 80 microfarad, R that is 40 ohm. A. Determine the source frequency which drives the circuit in resonance. Okay. Now, second question. Obtain the impedance of the circuit and the amplitude of the current at the resonant frequency. Determine the RMS potential drop across the three elements of the circuit. Show that the potential drop across the LC combination is 0 at the resonant frequency. Now see. We supply voltage that is 230 volt. Inductor that is with inductance 5 Henry, capacitor that is with capacitance 80 microfarad, so that is 80 into 10 raised to minus 6 farad, and R that is 40 ohm. Now at resonance, the angular frequency that is 1 upon root LC, so here substitute the value of L 5 and C that is 80 into 10 raised to minus 6 and solve it. You will get angular resonant frequency. Then resonant frequency that is omega 0 upon 2 pi. So omega 0 is calculated here. Divide it by 2 pi. You will get resonant frequency. Now at resonating frequency, we know this thing Xc that is equal to XL. So in that case, Z that will be equal to R. Now I, the RMS current, that is V by Z. But at resonant frequency, Z equal to R, so we can write V by R. So 230 by 40, you will get the current. Now see here, we have to find the amplitude of current. Amplitude means maximum value. That is the peak value of the current. Now I that is equal to Im by root 2. Therefore, Im that is equal to root 2 into I. Im itself is the amplitude of the current. So root 2 into here I that is 23 by 4 substitute, you will get the answer. Then potential drop across each element. So now current in the circuit I that is calculated 23 by 4 ampere. So potential drop across resistance that is IR. Substitute the value of I 23 by 4 and R that is 40. You will get potential drop across resistance. Then potential drop across capacitor. We see that is I into capacitive reactance. So Xc. So I that is 23 by 4 and Xc that now we have to calculate separately. Okay. Xc that is 1 upon omega C and you will get the answer. Then VL that is I into inductive reactance XL, XL that is omega L. Clear? So substitute the values of omega and L, you will get the answer. Now here when you solve this one, you will observe this thing VC and VL both will be same one. But This is the series circuit. So in series circuit, the current is the same one through each element. So if we think about the phasor diagram of voltage and current, then voltage across capacitor and inductor, both will be exactly in opposite direction, because with respect to current, the phase difference, that is plus or minus pi by 2. Clear? And therefore, when the magnitude of VL and VC, that is same one, so VL minus VC, that will be equal to 0. Clear to all of you? Example 7.12. An AC circuit contains a 20 millihenry inductor and 50 microfarad capacitor with an initial charge of 10 millicoulomb. The resistance of the circuit is negligible. Let the instant the circuit is closed be t equal to 0. A. What is the total energy stored initially? Is it conserved during LC oscillations? B. What is the natural frequency of the circuit? C. At what time is the energy stored? 1. Completely electrical, it implies stored in the capacitor. And 2. Completely magnetic, it implies stored in the inductor. D. At what time is the total energy shared equally between the inductor and the capacitor? E. If the resistor is inserted in the circuit, how much energy is eventually dissipated as heat? Okay. Now see, easy one but somewhat lengthy. Okay. See, inductor, that is with inductance 20 millihenry, so that is 20 into 10 raised to minus 3 Henry, and capacitor, that is with capacitance 50 microfarad, so that is 50 into 10 raised to minus 6 farad. Now Qm, that is given to you, that is 10 millicoulomb, so 10 into 10 raised to minus 3 coulomb. So question A. Now initially the total energy. So total energy stored initially means at time t equal to 0, that is the electric energy stored in the capacitor. So that is Qm square by 2C. Qm, that is 10 into 10 raised to minus 3. C, that is 50 into 10 raised to minus 6. All this one, you will get energy. And this energy will be conserved. We discussed in the theory. Okay. Then question B. The natural frequency of the circuit, that is 1 upon 2 pi root LC, substitute L equal to 20 into 10 raised to minus 3, and C, that is 50 into 10 raised to minus 6. And solve it, you will get natural frequency of the circuit. Then after C, at what time is the energy stored is completely electrical, and second completely magnetic. Now see, electric energy at any time t, that is given by Qm square by 2C cos square omega t. So when the value of cos square omega t, that is equal to 1, then the total energy that will be stored in the form of electric energy. So cos square omega t, that will be equal to 1 when omega t, that is equal to n pi, where n, that is 1, 2, 3 and so on. So for omega t equal to n pi, your cos square omega t, that will be equal to 1, and u, that will be equal to ue. Total energy, that will be equal to electric energy, or we can say total energy that is in the form of electric energy. Now omega, that is 2 pi by capital T into small t, that is n pi, pi cancel. So small t, that is equal to n t by 2. So substitute the value of n, 1, 2, 3, 4. It implies that at time small t equal to capital T by 2, capital T, 3 capital T by 2, 2t, at these time, the total energy in the circuit that will be in the form of electric energy. Then after, at what time the total energy is in the form of magnetic energy, that we have to calculate. So magnetic energy at any instant, that is qm square by 2c, that is sine square omega t. So here when sine square omega t that is equal to 1, then total energy that will be in the form of magnetic energy, and that is when omega t that is 2n minus 1 pi by 2, because sine pi by 2, sine 3 pi by 2, sine 5 pi by 2, sine 7 pi by 2 all give you the value 1 or minus 1, and square of it will give you resultant 1. So for omega t equal to 2n minus 1 into pi by 2, where n equal to 1, 2, 3, your total energy in the circuit will be in the form of magnetic energy. Now, omega that is 2 pi by t into small t, 2n minus 1 pi by t, pi cancel, so small t that is 2n minus 1 capital T by 4. So small t equal to t by 4, 3t by 4, 5t by 4 means at these time, means at time t by 4, 3t by 4, 5t by 4, the total energy in the circuit that is in the form of magnetic energy. Clear? Then question D. At what time is the total energy shared equally between the inductor and the capacitor? Shared equally, it implies that the electric energy and magnetic energy, that is same one. So at any instant, we can write electric energy, that is qm square by 2c cos square omega t, and magnetic energy qm square by 2c sin square omega t, and compare these two. So cos omega t equal to sin omega t, and that is possible only when omega t equal to pi by 4. Again substitute omega, that is 2 pi by t. So pi cancel. Therefore, small t that is equal to t by 8. It implies that here at t by 8, 3t by 8, 5t by 8, at this time, your electric energy that will be equal to magnetic energy. Then, if a resistor is inserted in the circuit, how much energy is eventually dissipated as its entire energy? If resistor is connected, total energy will be dissipated in the form of heat after some time. Clear to all of you? 7.13. A coil of inductance 0.5 Henry and resistance 100 ohm is connected to a 240 volt and 50 Hz AC supply. A. What is the maximum current in the coil? B. What is the time lag between the voltage maximum and the current maximum? Okay. Now see, L that is 0.5 Henry. Then V that is 240 volt. Resistance in the circuit is 100 ohm. Frequency of the supply that is 50 Hz. Now maximum current. So that is Im equal to Vm by Z. But maximum voltage is not given to you. RMS voltage is 240. So Vm that is root 2 into V by Z. Now here in the circuit, L and R are connected in series. Capacitor is not there. So as per equation, Z equal to under root R square plus Xc minus XL whole square. Xc is not there. So resultantly, we can write Z that is under root R square plus XL square. Now, XL that is equal to omega L. Omega that is 2 pi F into L. So now substitute the value of F and L, we will get XL. And once we get XL, then substitute here the value of R 100 and value of XL, and then solve this one, you will get Z. Now Z is calculated, so we can calculate Im, that is root 2 into 240 upon value of Z, we will get the current. Now phase difference, 10-5, that is XL by R. So substitute the value of XL here, and then R, that is 100, solve it, and from that find out phi from the table of natural tangent, and you will get the phase difference between voltage and current. Now from that you have to calculate the time lag or time difference. So when 2 pi radian is the phase difference, the time difference is capital T. Capital T, that is the periodic time one cycle is completed. Clear? So 2 pi radian phase difference correspond to capital T time difference. So phi radian phase difference correspond to how much time difference. So small t, that is phi t upon 2 pi. We can rewrite this one as phi upon 2 pi by t. But 2 pi by t, that is omega. So you can write t, that is phi by omega, or you can write phi upon 2 pi f. Now substitute here the value of phi, which one is calculated here, and f 50, that is given to you, and then solve, you will get the time difference. Clear? Then example 7.14. Obtain the answer A to B in exercise 7.13 if the circuit is connected to a high frequency supply, 240 volt, 10 kilohertz. Hence explain the statement that at very high frequency an inductor in a circuit nearly amounts to an open circuit. How does an inductor behave in a DC circuit after the steady state? Clear? Now see V, that is 240 volt. Now frequency, that is very high frequency, 10 kilohertz. So that is 10 into 10 raised to 3 hertz. Now in this case, if we calculate the inductive reactance XL, then XL, that is 2 pi FL. If we substitute the value of F and L here, then we will get XL, that is 3.14 into 10 raised to 4 ohm. Tremendous large resistance offered by inductor to the circuit. Okay. So now if we calculate Z, that is under root R square plus XL square. So your Z, that will be also large one. Now if you calculate again the maximum current, then that is root 2 into V240 upon Z. Now if you substitute value of Z here, then your current, that will be very less. So you can say that is nearly equal to 0. And when the current in the circuit is nearly equal to 0, it implies that we can say the circuit behave as open circuit. So you will get the open circuit condition, because in the circuit you will not get the current. Okay. Now for DC supply, inductor simply behave as a conductor. Simple conductor જેમ હોય એમ જ એની behavior હોય. Clear? Example 7.15. A 100 microfarad capacitor in series with 40 ohm resistance is connected to a 110 volt 60 hertz supply. Then question A, what is the maximum current in the circuit? B, what is the time lag between the current maximum and the voltage maximum? Simple. Capacitance in the circuit, that is 100 microfarad, so that is 100 into 10 raised to minus 6 farad. Resistance, that is of 40 ohm, supply voltage 110 volt with frequency 60 hertz. So to calculate the current, first of all, we have to calculate the impedance Z. Now, impedance Z, that is under root R square plus XC square. So here, first of all, calculate XC. XC, that is 1 upon 2 pi FC. So 1 upon 2 pi F, that is 60, and C, that is 100 into 10 raised to minus 6. So we can directly substitute as 10 raised to minus 4. We will get XC. Then in the equation of Z, under root R square plus XC square, substitute R, that is 40, and XC that we calculated here, substitute its value, you will get Z. Now IM, maximum current, that is VM by Z. VM, that is root 2 into V by Z. So root 2 into 110, Z we calculated here, substitute its value, and then solve, you will get IM. Now, time lag. So in previous example, we discussed T, that is phi upon omega, or we can write that is phi upon 2 pi F. Now, phi is not given to you. So first of all, we have to calculate phi. Phi, that is tan inverse XC by R. XC is calculated, R, that is 40. So calculate phi from the table of natural tangent, and then after substitute that particular value of phi here, and then F 60, and solve this one, you will get time lag. Clear to all of you? Then after example 7.16, obtain the answers to A and B in exercise 7.15 if the circuit is connected to 110 volt 12 kilohertz supply. Hence explain the statement that a capacitor is a conductor at very high frequencies. Compare this behavior with that of the capacitor in a DC circuit after the steady state. Very simple. V, that is 110 volt frequency. Now that we have to take 12 into 10 raised to 3 here. So first of all, calculate resistance offered by capacitor to the circuit, that is capacitive reactance. That is 1 upon 2 pi FC. If you substitute here F and C, then we will get XC, that is very, very, very small. So if XC is very small, then we can say for this particular supply, which one is with very high frequency, capacitor will behave as a conductor because it is offering very, very, very less resistance to the circuit. But if we think about DC, then for DC, frequency is 0. So capacitor offer infinite resistance to DC supply. So when capacitor is connected with DC, always it behave as insulator. Clear to all of you? Example 17. Keeping the source frequency equal to the resonating frequency of the series LCR circuit, if the three elements L, C, and R are arranged in parallel, show that the total current in the parallel LCR circuit is minimum at this frequency. Obtain the current RMS value in each branch of the circuit for the elements and source specified in exercise 7.11. So the values of R, L, and C that we have to take from example 7.11. Now see, let's prepare the phasor diagram. So this is the parallel combination of L, C, and R. So we know this thing in parallel combination, the potential drop across each element will be same one, but the current will be different one for each element. So here now to prepare the phasor diagram, we will consider the voltage phasor as the reference. Take it on x-axis. So this is voltage phasor, and that is same one for all. Now in case of resistor, there is no phase difference between voltage and current. So current phasor for resistor is represented in the direction of voltage phasor, and current through resistor is suppose IR. So this is IR phasor. Then after, if we think about capacitor, so for capacitor, current lead the voltage in phase by pi by 2. So here the current phasor of capacitor, that is represented pi by 2 ahead, means on positive y-axis here. Then in case of inductor, the current lag behind by pi by 2 in phase with respect to the voltage. So current phasor for inductor, that is represented at minus pi by 2 with respect to voltage, therefore on negative y. So now the resultant current, that is IL minus IC. So now this IR and IL minus IC will give you the resultant current, that is I. So from this phasor diagram, we can write I, that is under root IR square plus IL minus IC whole square raised to 1 by 2. So IR, I, that is V by R. Now here we can substitute IR, that is V by R, so V square upon R square. IL, that is V by XC, so IL, that is V by XL, V by XL, and IC, that is V by XC. So substitute all values here, take V common and take it outside the bracket. So we can write I, that is V into 1 upon R square plus 1 upon XL minus 1 upon XC whole square raised to 1 by 2. Okay. Now here we want to calculate, obtain the current RMS value in each branch of the circuit. So IR, that is V by R. So V and R, that we have to take from example 7.11. So their value of V, that is 230, and R, that is 40. Substitute, you will get the answer. Then IL, so current through inductor branch, V, that is 230, L, that is 5 Henry. Substitute, you will get the answer. Then XL, that is 2 pi FL. Here first calculate XL and then substitute, you will get the answer. IC, that is V by XC. So V upon XC, that is 1 upon 2 pi FC. So separately calculate it by taking value C, that is 80 microfarad. XC calculate, substitute it here, you will get the answer. And then at resonance, Z, that will be equal to R. Clear? So at resonance, when Z equal to R, it implies that here the impedance of the circuit, that will be maximum 1. So from this equation, you can understand this thing. When your impedance, that is maximum 1, then current, that will be minimum 1. Clear to all of you?